Last week we finished the Bose gas and we obtained 3 behaviors. So we noticed that I will start with the last one, the behavior of the heat capacity. So this is Cv as a function of T. Looked like a lambda letter, and it's called the lambda transition. This peak is around a specific temperature we call Tc. Okay. We obtained this behavior theoretically from looking on the energy as a function of temperature. And the energy as a function of temperature behaved like this. Okay, so the slope was almost or practically diverging, again, at this specific point Pc. So all those look somewhat peculiar, okay? And the explanation, we knew, we actually started with this and ended with the lambda transition, and the explanation all comes from the behavior of the occupation of the ground state. This is not something that one can measure. One can measure the capacity, one maybe can measure the energy, but the occupation of the of the ground state, N0 average divided by N average as a function of temperature, looked like this. So it was 0, what wasn't negative, exactly 0, and up to a specific temperature, Tc, and then it started to rise. The reason for all those peculiars lies in this plot over here. Bose gas. And this is what we call Bose-Einstein condensation. Below a specific critical temperature, call this Tc, that for the Bose gas, without any interactions, will depend only on the number, on the temperature and the number of particles that you're pushing inside. And if we have to work in the thermodynamical limit, if you're not working in the thermodynamical limit, there is no sharp transition. Everything here is smeared. We obtain that a macroscopical portion, and that's important that it's a macroscopical, okay? A macroscopical portion of the particles sits in a microscopical energetic level, okay? This is what explains all those interesting behaviors. Okay? So it is the accumulation of many particles. If you want to think about it, the contribution is of a one single state is not negligible. Okay? In usual cases, when we deal with macroscopic number of states, macroscopic number of energetic states, and macroscopic number of particles, contribution of each single state is negligible. It's just accumulations of the many that produces the physical behavior. Here, something completely different happens. Okay? This is why it's extremely interesting. One single state contributes disproportionately to, well, we call it its size. So this is the interesting physics. But although it momentarily reminds us that something that's related to the phase transitions. We started this class almost 3 months ago by talking about thermodynamics, and the thermodynamics is a continuum transition from one state to another, but the matter sometimes performing switches from one state to another in a, well, we call it discrete way, but a very fast way. We call it a phase transition. Okay. Now this reminds us somehow of those phase transitions that we have seen. Right? Mathematically, at least, we have a critical temperature, something switches, okay, and the behavior becomes completely different, at least at this part. Okay. But there are two buts. First but is the phase transition that we discussed before were first order phase transition. There was a jump. Okay. Here, absolutely no jump is observed, right? So it is 0, 0, 0, and then it started to rise. All right. So the derivative performs a jump in this point. Okay. But the quantity itself, there is absolutely no jump. So we can say, well, maybe it's a second order phase transition. Remember, there are orders. The first order phase transition is the quantity, the observable itself, performing a jump. Usually looked on the volume or the entropy. Here, the occupation number does not perform any jump, but its derivative will perform a jump. So maybe it's a second order phase transition. This is the first but. Second but is when we spoke about phase transitions, we said the following. Phase transitions originate from interactions. Here, there is no interactions between the particles, right? So the particles do not interact at all. Okay? So it's a boson gas, so bosons. There is even no Pauli exclusion principle. They can occupy any level that they like, but still somehow this phase transition occurs. Okay? So still no interactions, but this is the quantum nature and the principles of the ground state, right? So although there is no interactions, so it's maybe second phase or transition, and there are no interactions whatsoever, still something that is reminiscent of the phase transition behavior happens over here. Now moreover, very similar behavior to this one was observed for magnetic systems. And in magnetic systems, the experiments were performed by Pierre Curie, the husband of Marie Curie. She is much more famous than he is. They work together on some of the properties. And Pierre Curie measured magnetization properties of different systems. Okay. Now, there are, vaguely speaking, a distinction between paramagnetic and ferromagnetic behavior. What is paramagnetic? Paramagnetic is a system that absolutely has no internal magnetism. Okay? So most of the systems are non-magnetic. They do not act as a magnet. Ferromagnetic behavior is when a system has self-magnetism, okay, and it acts as a magnet. What Pierre Curie discovered is the following thing. You take a system, not every system, but many different systems, metallics mostly, and this is the temperature. This is the temperature. And you apply no external magnetic field. Okay, that's important. Because the moment that you apply magnetic field, system somehow responds and some magnets occur. But that you do not apply any magnetic field whatsoever. And you measure the magnetic moment of the system. Again, you do not look on one single atom. It's a macroscopical system. And something interesting occurs. You measure it and 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 measure it till you reach a specific temperature. Now, we call it TC, TC, and TC. Here we also call it TC, but not just because it's T critical, but it's because of T Curie. Okay. What happens after T Curie? Two things. Sometimes the magnetic moment starts to rise, and sometimes it's going to be positive, and sometimes a magnetic moment will become negative. Okay. If you know what bifurcation is, it very much looks like a bifurcation. Okay, so this behavior very much reminds us of this behavior over here. But This was observed way before Bose gas, right? And this was the first one. So, and there are no ideas about bosons, and even not a lot of ideas about quantum physics at all, but this is also some sort of a display of phase transition behavior, because the properties of the system turn swiftly from paramagnetic, paramagnet, and a ferromagnet. So you take a system, you cool it down, and whoop, it becomes a magnet. Out of nowhere. So here you take a system, you cool it down, and oops, the occupation starts to rise. The physics is very different. The mathematics a little bit similar. Here, absolutely no interactions between the different particles. It's just the interaction of the particle and a single state. Here, as we will see, the interactions are crucial. Extremely crucial. Okay. So what we are going to do now, we're going to treat the last subject of this class, and this is magnetic systems and order-disorder transitions. Order, disorder, phase transitions. All right. Now, this is not the only thing that Pierre Curie noticed. So, for example, he noticed the following thing: if you apply an external field, so here the system somehow chooses. It's not clear how exactly, but it somehow chooses to become either positive magnet or negative magnet. So you can take the system, you cool it down, okay, it becomes a positive magnet. You then heat it up, you wait, you cool it down again, and it becomes a negative magnet. And you can do it a lot of times. So sometimes it's positive and sometimes it's negative. Sometimes it's positive and sometimes it's negative, okay? So something interesting going on. Another thing that Pierre Curie noticed, that if you take a ferromagnet, or paramagnet, paramagnet, and you plot M as a function of your external field H. Now, so if it's a metal, some sort of metal, the H applied to external field, there are different spins around it, or self-magnetations of different particles, and they try to align according to external field. Okay, so what we see is that the magnetism of the system, magnetic moment of the system, it grows over here, and decays in this direction. So if you apply, eventually it will saturate. So if you apply an external field, you're going into this direction. What will happen is your magnetic moment will also grow. Okay. So you're walking in this direction according to the increase of your external magnetic field. So you increase the magnetic field, the magnetic moment grows. Then you increase your magnetic field, the magnetic moment is growing. And this is what you obtain. Now you reach this point, and then you turn the direction of the sweep. So instead of, you're over here. This is your magnetic field over here. And then I'm saying, well, I want now to turn the magnetic field down. I want to decrease it, the external magnetic field H. Okay, so what will happen what will happen is that it will go the other way around. Okay. You will go over here. And as you decrease and decrease your magnetic field, eventually you'll reach this another saturation. Then you can play the same game. So I'm over here. Let's now increase the external magnetic field. Then you grow back again. Okay? So nothing unexpected happens. You go forward in the magnetic field, you go backwards, and the magnetic moment rises and decays, rises and decays. So it exactly follows the external magnetic field. So this is the paramagnet. If you do it for a ferromagnet, something different occurs. So if you do it for a ferromagnet, so first of all, this is M, this is H. So first of all, the magnetic moment already had some specific magnetization. Okay? So you see it over here, the ferromagnet, it has a self-magnetization. So let's assume that this self-magnetization, it's a negative from positive pole to negative pole. So this is your self-magnetization. Now you start to increase your external magnetic field. All right, so you're increasing your external magnetic field, and the self-magnetization have to grow because of the increase in the external magnetic field. All right, so it grows. At some point it will cross the zero line, and eventually it will reach a saturation. Okay, great. So you're saying, so the game that I played, I increased my external magnetic field, the magnetic moment, self-magnetic moment have grown, and I reached the saturation. Okay. Now, you're playing the same game as you played for the paramagnet. You start to decrease the external magnetic field. So what will happen? You're growing now in this direction. And instead of following the same line, okay, as for the paramagnet behavior, you're doing something like this. Okay? You're doing something like this. So you are not going backwards to your original magnetization even for the zero external magnetic field. You're doing something like this, like this, like this. Okay? So it actually very much depends on which direction you push your external magnetic field. Now you say, okay, now let's go backwards again. And instead of following the same line as for the paramagnet, you're creating a new line. Okay. And then the loop is closed. Okay? So you're going in this direction, you set over here. You're decreasing the H, you go from the other way. This is the hysteresis loop. It occurs only for ferromagnets. Okay, so something very, very, very much different occurs in this part and in that part. Okay? So we won't describe exactly the dynamics of the hysteresis loop and why it occurs, mainly because it's a dynamical feature, and we're mostly interested here in statics. But remember, when you have this, it's an indicator of memory. Okay? So it basically says that the system remembers the initial state. Here the system absolutely doesn't care about in what state it was created. Okay? I was created in the positive magnetization, I will go to zero. I don't really care. Here, it very much cares where it's coming from. So the history, it's very much important for ferromagnets. Okay. We want, and now history and memory, it's something that's related to time. We won't describe it because everything in this class is about statics eventually. But this is a very important feature of the transition for paramagnet and ferromagnet. We mostly concentrate on this feature. Okay? So the self-magnetization, it's important that here H equals 0. Self-magnetization, even when you have an zero external magnetic field, it's accumulating somehow a non-zero magnetic moment, self-magnetic moment, as you lower the temperature. Now, so this is T Curie, and we want to be consistent with the other TC that we've seen before in this class, so we just call it TC. Remember, it's T Curie. Pierre Curie, smart, important guy. His wife, Marie Curie, was even smarter and more important. All right. So what we are going to do, how we model this behavior. Because, oh, it's nice. Those are experimental facts. How are we going to model this? We focus on the transition from paramagnet and ferromagnet, and we want to focus on the behavior of the magnetism itself. And why? I called it order and disorder. So what's the idea? Where the magnetism is coming from? So there's a lot of electrons sitting on atoms, but eventually, and there are external states, and etc., 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 but you can understand this very oversimplified that you have a box, so this is my metal, this is my material. Each atom eventually have a spin, right? Now, the most contributing factors to the spins are the exact, not almost 3 electrons, but the electrons that are sitting in the external shells, all right? Because all the other spins are somehow cancel out each other. And eventually, if I'm looking on different atoms inside the system, each atom, somehow, we can plot it as a vector, and this is the self-spin of each atom. The orientation of the spin, at least in the paramagnet state, is absolutely random. Okay? So this is paramagnet. Paramagnet. The orientations of all the different spins are absolutely random, and eventually, when we measure all the different spins, so what is, this is SR, this is SR prime, this is SR prime prime, etc., etc. So we have different positions of different atoms. Each single atom has a specific spin. When we measure the total magnetic moment, it's just the summation of all the possible R's, which are vectors, of SR, and we measure all the different spins inside the system. Okay. I'm not going into the details how exactly we measure it, but this is what we measure. Okay. Now you can say Stas, and when those guys are random, but they are also fluctuating, right? So if I have a total spin, something happened to the atom, the spin goes a little bit up, a little bit go down, or it flips exactly the other direction. So what is this? Those are random variables. So this is also a random variable. We can plot it like this, M. And that's, for example, if I want to measure the mz, which is m multiplied by z hat, okay? Because I want to talk about eventually scalars and not vectors. So when I'm looking on this mz, as a function of time, so I can measure at the beginning of my experiment the magnetic moment. I wait a little bit, I measure it again. I wait a little bit, I measure it again. I wait a little bit, I measure it again. And I repeat those measurements many times. Okay? Why? Because like I told you, all those SR can modify their orientation. Now what happens in the paramagnet, because of all the different symmetries, there are no prescribed direction. Okay? There are absolutely no prescribed direction of where to follow. What happens is that this mz fluctuates around 0. This is the symmetry. Due to the symmetry inside the system, what I mean by symmetry, I don't have a prescribed direction. I can point over there, I can point over here, I can point over here, and I can point in this direction. Due to the symmetry inside the system, the magnetization is simply 0. Okay? So this is paramagnet. All of this. Now, if I apply an external field, think about it. If I apply external field, the energy is equals to minus mu multiplied by h. What is mu? The magnetization of a spin, so ES is the magnetization of the spin multiplied by the external field, dot. Okay, so it's a scalar. Why the minus sign? Because the spins like to be aligned. This is the external field spin interaction. The spins like to be aligned with the external field. All right? The more they are aligned, the lower is the energy. It's a more preferable situation. We know that. Low the energy, more preferable situation. So when you apply external field, each spin, you break the symmetry. Okay? When you apply a specific external field, you break the symmetry. Okay? So this is symmetry.
It's a with the y, not I.
Okay. And this is also y?
Yes.
Yeah, okay. Symmetry breaking by external field. So what happens when you break the symmetry by external field? This is your H, all right? You have different atoms or molecules. Although they can fluctuate, we know, because they can prefer many different states, but big portion of them will prefer to go or to be directed in the direction of the external field. Okay? So what we have a preferred direction. Okay? Due to the external field, we broke the symmetry. There is a preferred direction. What is the preferred direction? The external field is the preferred direction. Great. So some of them will still point from time to time in the different directions, right? But there's still a preferred direction. Where? Over there. Why? I broke the symmetry. Okay, so if we now look on mz as a function of t, so instead of looking 0, 0, 0, 0, 0, right, we will have specific number which is defined by the temperature, by the h, and this mu s over here, right? And in general we have fluctuations. Let's call it some mh, and here is 0. Right? And moreover, you could turn on this external field at some specific point of time. So it goes 0, 0, 0, 0, boom, you turn the external energy h, it was 0, and somehow it became a non-zero number, and we'll observe a jump to a non-zero behavior of the magnetic moment. Why? This is why. The energy, before the energy was independent of the field, because the field was zero. Somehow you have a preferred direction, symmetry is broken, but you broke the symmetry. Okay? So this is still paramagnet behavior. What happens at the ferromagnet case? There, again, H equals to 0. You have no preferred direction whatsoever inside the system. The expectation for any kind of material is something like this will happen, right? That something like this will happen. So you plot, if you have a microscope, you can look on each and specific spin inside the system. You say, well, this is what I expect. I have different molecules, atoms inside the system. Okay. And somehow, for ferromagnet, H equals to 0, E lower than Tc. You will start to see, let's make it lower and lower than Tc. Somehow, they all point exactly in the same direction. It does not have to be up. Or maybe some of them still pointing down, right? Or to the right. But the majority, or a macroscopical portion of them, point exactly in the same direction. Okay. H equals 0. There is absolutely no preferred direction whatsoever, but somehow they organize together. They organize together and they point in some direction. So this is spontaneous symmetry breaking. Okay. Yes?
When the spin points down, this is called negative position.
So it depends on what is exactly this guy, right? If you have external energy. Here, the negative, it depends how you define what is positive and what is negative. Yeah. But they can point in any direction. So here I choose up, but actually they somehow organize and they choose a specific direction which can be absolutely random if it's a three-dimensional. So they can point up, down, towards you. The point is they all pointing together. Okay?
So if I choose that up is positive, then I'm negative?
Yeah. It depends on how you define what is positive and negative.
So I have another question. At the beginning of the lecture, you showed us a graph of the magnetic moment versus the temperature, right?
Mm-hmm.
And you told us that when you make the spin, when you hit the system, you make like this.
Either positive or the negative, right?
Yeah. My question is, when you scramble the spins, then there is no magnetism, right?
Yep.
So, what makes the system preserve the memory when you first spin up and then you hit it, and then it goes to when you cool it down, it goes for spin down.
Okay, so yeah, I understand. So remember what I told you. I can heat it up, cool it down, heat it up, and each time I will get either positive or either negative, and it's the initial configuration exactly at the point when I'm making my temperature Tc. So the system is somehow like this, right? But if you look on the fluctuations, there is a microscopical preference to point out, up, or point down. Look at this, it goes up, down, up, down. So that's always small fluctuations. So it will choose either to point up or either to point down. So I plotted this as up. Maybe because when I cross Tc, just at this point when I cross Tc, the system was over here. There was microscopical preference to point up. This microscopical preference will make eventually all of them point up. Okay? So this is something kind of initial conditions. The initial conditions is never exactly zero because it's a macroscopic system. When I say it's t equals 0, it's not 0. There is always some preferences, small fluctuations. Those initial conditions eventually will affect where you go. Okay? Now let me continue a little bit. So what I want to say is the following. Why it's spontaneous? Spontaneous, no preferred direction. It does not, and it's related to your question, it does not always choose exactly the same direction. It can choose up, it can choose down, it can go backwards, it can go towards you, right? It is based on the initial conditions, right? But it's always spontaneous. And why it's symmetry breaking? Because if you shift your temperature high enough, there is absolutely no preference to any direction. So where it's coming from? Where is this behavior coming from? And so if I measure over here this m as a function of the temperature, I know that at T Curie goes like this, goes 0. What I measure here is this point. I can heat the system up, cool it down, and maybe eventually they will point all downwards and I will measure this point. I never know. I never know. It can be upwards, it can be downwards, I don't really know. But I know that they somehow break the symmetry spontaneously and create a system where everybody are organized. Now you can ask the following question, where is this graph? That reminds us of this, it reminds us of what? Of this Bose-Einstein condensation. So what, there is a preferred energy and those are bosons and so the answer is no. In this system, there are interactions, right? You know that there is something that's called spin-spin interaction. So great, the energy is this guy, right? So the energy of a specific spin is this contribution. But here, that it's never enough. The energy is minus mu s of a specific spin. Mu s multiplied by h minus, okay, 1/2 a summation of all the other spin s prime j s r s r prime. Call it r prime. R minus r prime. They interact. All the different spins somehow interact. So I plotted here as energy of a single spin, right? The different spins, all right, this is interaction with the external field, but all the different spins feel each other and they somehow interact. You can say, oh, it doesn't make any sense. It doesn't absolutely make no sense because, okay, so I have an interactions, right? But, all right, so what are the interactions? The interactions, when I write it in this way, and J, the interaction term, is positive. So all the spins, they prefer to point in the together. So if I take two spins, okay, the coupling, the interaction coupling, this is the interaction part. Interaction. I take two spins, this one and that one, and due to the interaction, so let's assume that h equals 0, and due to the interactions, they prefer to point in the same direction. This guy points upwards, and this guy would also point upwards. All right, so those guys pointing in the same direction. All right, let's take another spins, this guy and that guy. They interact more strongly with each other, and they will prefer to point in that direction. And I will take another pair, and they will prefer to point in that direction. The symmetry, when I'm looking on this, the symmetry should be preserved. Some of the guys who point over there, they interact between each other. Some of the guys who point over there, they interact between each other. why the symmetry should be broken. And their answer is, it's not a natural outcome. Okay? This is a phase transition. Somehow, the interactions spread out eventually far enough such that everybody are talking together and everybody prefer to go this or that or here. So the naive expectation when we look on this is that, well, the symmetry should be exactly the same. But the reality, and we'll solve it in a simplified model called an Ising model, although it's not Ising who invented it and not Ising who solved it, but we call it still the Ising model that describes this phase transition. Okay? And we will see that the interactions are the sole component that leads to this spontaneous symmetry breaking. Okay? Without any interactions, you won't have any ferromagnetism. When you have interactions, somehow those interactions become strong enough, but only in the low temperature limit, and there, and only there, all the guys try to follow exactly the same direction and the symmetry is broken. How, what, why? We will see tomorrow in the lecture. Thank you all.
סטאס, אבל ברזל הוא לא פרומגנטי תמיד?
יש כאלה שכל הזמן פרומגנטיים, זה מאוד תלוי בסטרוקטורה, קובי, לא קובי, בלה בלה בלה. זה מאוד תלוי במבנה הסריגי. יש כאלה שכן, ויש כאלה שלא. ויש כאלה שתתברר אותם, והם יהפכו להיות פרומגנטיים. כי כמו שאמרתי לך, זה לא בדיוק ככה, יש לך סריג. ומה יושב בסריג, ומה יושב בשכבות החיצוניות וכו'. אז יש כאלה שכן, ויש כאלה שלא. זה תלוי במבנה הסריגי.